And happily, I would like to introduce you to Professor Otfried Gühne from University of Siegen, and he's going to talk about multi-particle quantum entanglement. So thanks. Thank you.
Okay, can you hear me? Yeah. Perfect. Good. Okay, so first I would like to thank the organizers for this nice conference, or nice school. It's a nice conference. So this is my second time in Brazil. So, but the last time was just 9 years ago. So that's why it's nice. And yes, so I will talk about multi-particle quantum entanglement, and this is the first of 3 lectures. Before starting, maybe just to show you a little bit where I'm from, because this may not so known. So this is Europe, yeah, and this is more or less the place where Siegen is. So it looks quite central, but it's more or less in the middle of nowhere.
Very beautiful, right?
Yes, the symbol is much bigger than the city. So if you zoom in a bit, it looks like that. Yeah, and yes, the city is actually not so big. And then, if you somehow zoom further in, it looks like that. And this is just my group, and you will maybe see some of these names in the references, because I will talk about some of the works that we did now. So, in general, I'm giving here 3 lectures about multi-particle entanglement, the structures of our planets and following. So, the first lecture today will go about pure states. The next lecture on Friday will be about mixed states. And finally, in the last lecture on Saturday, I will talk about some specific families of states like graph states and so on, which essentially go for more than 3, 4 particles and so on, to see some general structures. So this is my schedule for today. So today I want to talk first about some basic facts about bipartite entanglement, which in principle also Anna explained, but I just want to recall some basic facts which I will need. Then I will mainly talk about 3 qubits about the difference between so-called GZ and W states. I will explain what GZ means, what W means, where the letters come from, and so on. And yes, what are the properties. Then I will go beyond 3 qubits, mainly talking a little bit about this problem of so-called A and B states, absolutely maximally entangling states. And finally, I talk a little bit about quantifying multi-particle. And of course, I should say that this field of multi-particle entanglement is much too big, so I cannot cover everything. So it's just really highly selective. Yeah, and I should also say, if you have questions, please interrupt me at any time. Yeah, so this is just a plan, and I'm completely happy if I only do half of it, and if you have a lot of questions. Okay, good. Let's start. So let's start with bipartite entanglement. And actually, this is also, I'm showing you some picture of the area where we live. This is the biggest day, which is some artificial lake. Good. So let's start with some facts about bipartite entanglement. So in principle, the basic scenario, we have something, Alice and Bob share some state design. And we heard already from Anna's definition that some pure state is called separable if it's something like a product state. And sometimes I write it like this, sometimes I write it like that to stress that this belongs to Alice and this belongs to Bob, but this notation is of course correct. And if a state is not of this form. So, if you somehow look at, for some examples, this state, for instance, obviously separable because this is directly of this form. This state looks a little bit more complicated, but you can write it like a tensor product of this form, and then it's something like separable. And here are some entangled states. One of them is for this kind of Bell state, which will also occur later. And actually this state, which looks quite similar to this one, but there's only one minus sign, is also entangled. You will not be able to write it like that. It doesn't work. I should also say that you see already that often I drop the normalizations of states. Yeah, I hope you feel comfortable with that. Yeah, otherwise. Bad luck. Good. So, then, what are some basic properties of entanglement? So, first, entanglement is somehow always invariant under local changes of the basis. So, it doesn't mean this question of whether you can write a state like that, and all the properties that we're looking at on states are somehow independent under some basis change. So, if you rotate just single qubits or whatever by some so-called local unitary transformation, which does not I mean, entanglement is necessary for value inequality violation. This was actually discussed shortly this morning. So for pure states, it's equivalent. The state violates the value inequality if and only if it is entangled. For mixed states, it's not the case. Yeah, so they're essentially entangled states which do not violate value inequality. And also what was explained by Anna is something like entanglement often seen as something like a resource for things like teleportation and cryptography. I will not go into much detail of that. Actually, I will go in no detail of that. So we'll just talk about it. Yeah. So this is just something like a reminder, yeah, while one is interested in this point. And some popular states are so-called Bell states, yeah, which are also occurred in Anna's talk, yeah, which is some consistent states, and there are some more mixed. Good. Questions? Good. Then, another tool that will be actually quite important, also for my talk, is the so-called Schmidt composition. And Anna introduced it already, and she gave a proof, so I don't have to do that. So it's just a basic fact that if I have an arbitrary bipartite state, I can always write it in a way where I only have sum of one index. Yeah, so if I choose these spaces properly, and these so-called Schmidt coefficients they're real, they're positive, they're unique, and typically they're always decreasing the order. So S1 is the biggest one, S2 is the next to biggest one, and so on. This is a convention which I just typically take. I didn't write it here. And then you can ask, okay, how many terms do I need? This is called the so-called Schmidt rank of the state, R. Yeah, if it's a product state, you need only one term, and you can have more and more terms, and this corresponds to sometimes the dimensionality of it. And this will become better. Okay. Then there's a notion of so-called maximum integers. This will also become important in my talk. And I mean, one way to define it is something that you say a bipartite state is maximally entangled if these marginals, meaning with marginals I mean always the reduced density matrices, if they are maximally mixed. Yeah, and this means that here if I trace it out, it's more or less 1 over identity. And in terms of the Schmidt coefficient, it means that they are more or less always 1 over square root of d. D is the dimensions, considering d times d system. Yeah, and the maximally entangled states are then, for instance, like the Bell states, or in higher dimensions, something like this equal superposition of these product states. Questions? Okay, good. So let's start with Zwickmühlen. And this is the castle also close to Siegen where we did our group routine. So let's start with multi-particle entanglement. I mean, multi-particle entanglement, we only have three parties, typically called Alice, Bob, and Charlie. And they share some quantum state. And now you can have different scenarios for this quantum state. So, I mean, there are just some simple things that you can write. You can write down a state that is called fully separable, which is something like the best analogy to a product state of bipartite system here, where just everyone has its own qubit and now there's no superposition of different terms. This is boring. Then there are things that are called biseparable, where you maybe have, for instance, that there's some entanglement between Bob and Charlie, there's some Bell state, and then, but Alice is somehow separated, yeah, this is just by this tensor product sign, meaning that there's some entanglement definitely in the state, but Alice does not take part, so that's why it's called biseparable, meaning there's some bipartition, yeah, where you can cut the system and there's no entanglement. It's a different class state. But then finally there are states which are not of this form, and these are for two examples, and this is one course called the GZ state and the W state. Again, not normalized. The GZ state, and the point is for me that both you can see as some generalization of Bell states. Because we can say, well, if I just drop here this 0 and this 1, then I get one of the Bell states. And I can also say see this as a generalization of Bell states because I have this one Bell state which is 0, 1 plus 1, 0, just extending it to a third party, and then I have 3 superpositions. So I mean, starting from the notion of Bell states, and we know that Bell states are important somehow, that you can say, I mean, both states are completely natural extensions of them. And the question is now, and this is actually the main part of this part of my talk, is what's the difference between these two states? Actually, during that I will mainly focus on the qubits, but during that you will learn a lot about other things that later become important for 4 qubits, 5 qubits, whatever higher systems. Okay, let's start. So I thought in the beginning that somehow this entanglement should be invariant under local unit terms, under the local chain of the basis. And so the natural question is, well, maybe these guys are equivalent, and then everything would be solved because, I mean, they would be more or less the same. But they are not. And how can you see that? Okay, you can try to find a basis chain from here to here, and you will just fail. But this is, of course, not the proof. But the main thing how to see it easily is just by looking at the marginals. Again, by looking at the reduced single qubit density matrices. Yeah, for instance, if I take here from GZ state, trace out Bob and Charlie and look at the reduced set on LSO, then it's this state. Yeah, which is actually a maximally mixed state. And if you do the same for the W state, you get this state, which is not maximally mixed because you have these factors 2, 3, and 1 over 3. So the eigenvalues of these states are different, and this you cannot neglect, or this means that there is no local unitary transformation connecting this state to this state. So with this you immediately see that they are not locally unitary. Okay, not much so far. But now we may ask, okay, now we have this local unitary equivalence, and before I told you about the Schmidt decomposition, that this is something like, okay, you can make by appropriate basis changes or by appropriate local unitary transformations, you can try to bring a state into this form, into this Schmidt decomposition. Then we ask, oh, how can I do this for multi-pattern systems? And if you, well, you can ask this, but unfortunately this is not possible. So the first thing that you have to remember if you go to multi-pattern systems, there is no Schmidt decomposition for multi-pattern systems. Yeah? So there's nothing in this generality. And what would Schmidt decomposition mean? Schmidt decomposition is to mean that you have something which consists only on 0, 0, 0 and 1, 1, 1, 1, 1. So more parties and more ones or higher dimensions, more and more indices or so. This is not possible. Which is actually also quite easy to see, because if you would have such a decomposition, this would be also a bipartite Schmidt decomposition. And a bipartite Schmidt decomposition is unique, and it's for general states this will not be a product state. This was on old argument and so on. But still you can ask, how much can I simplify a state? Yeah, and for 3 qubits, this is more or less right? That if you take an arbitrary 3 qubit state and apply local unit terms, then you can make it so simple that it only consists of these 5 terms. You have essentially these 5 lambdas, of course they're normalized, yeah, so effectively you have 4 parameters, and you have 1 phase. Yeah, so you cannot avoid some complex.
Why is the phase exactly there?
Why is it? It's a matter of convention a bit. So I mean you can see that this whole statement is derived from something like a bipartite Schmidt decomposition, because you have a 0 and something on Bob's Charlie, and you have a 1 and some other state on Bob Charlie, because these are the terms with a 1 always. Then you can ask, okay, what can I still have as a freedom to simplify it? But that's the phase at this term. I think you can safely also put it to some other terms. Yeah, so it's not unique that it has to be existent. And the point is there are other forms or other normal forms under local unit terms. Yes, this is not the only one, but this is the most common one. And the phase may then disappear somewhere else. But the important point is there is some complex phase. Yeah, which is not the case for the bipartite case, because in the Schmidt decomposition, everything is real. Yeah, but this is good. Okay. So this is sometimes called, or maybe I will call it later, something like a Schmidt-like decomposition. But be careful, this is not Schmidt decomposition. And I should also give you later some arguments that you cannot do similar things for multi-party systems. You will fail even worse. Yeah, if you go to more beyond 3 qubits, you will fail. Yeah, even worse. Good. Good. Questions? So, now let's talk about the notions of local operation and classical communication. And local operation and classical combination is somehow these things that you can, in some sense, easily do because you just do local operations and classical communication. What does this mean? And of course, with these operations, you cannot generate some intent. What does it mean? So, actually, you can view any of this LHC transformation as a protocol where you do as a sequence of the following steps. So either one party adds something like an ancilla system, meaning adding some extra qubits, or the party applies some local unit transformation, maybe on this main qubit, but also together with an ancilla qubit, but just on his or her part. And the other thing that is allowed that Alice or Bob may perform some measurement and then communicate the result. Yeah, so and this is something like an iteration of these steps. So you may see it like that. You start with some bipartite state as an input, then Alice does something, communicates the result to Bob. Bob does something, communicates the result to Alice, and so on. And you iterate and you iterate. The question is, what can you get as an output on these transformations? I mean, actually the scheme is physically quite clear. Yeah, because you have these three operations, you have clearly the sequence, and so on. Unfortunately, from a mathematical point of view, this is horrible. Yeah, I mean, classifying or characterizing all the possible LHC transformations is more or less impossible. Yeah, and that's why if people do something that I want to prove something, that something cannot be done by LHC, you typically take something like supersets, which are easier to characterize. You take a larger set of transformations, which you can, where you can show, okay, these are at least easy to write down, but they are strictly larger, but if I cannot do with a strictly larger set, then I can also not do it with a small set. And the mathematical problem is that actually these protocols may require really infinitely many rounds. So there's no constraint to having, I don't know, there's something like 6 rounds. Yeah, you can do more and more and more. And that's of course mathematically not so easy.
Question?
Yes?
So you say it consists of applying local unitary transformations, but we learned that like quantum channels would be the extension to it. Are there like something like local quantum channels that could be also in this category? Or?
Yes, actually local quantum channels you can always view as adding some ancilla plus making a local unit. Yeah, so that's nice. Yes?
When you say the protocol may take infinitely many, you mean it's unbound, the number of rounds?
Yes.
Or it's like a sequence and you take some kind of convergence or something like that?
No, it's mean like it's not a sense of convergence. You need infinitely many rounds to reach a certain result. The example is known where, for instance, for certain state discrimination problems where you need this. It essentially always makes this rounds into rounds, and there's a finite property you stop, but to make a perfect state discrimination, you have to make really an infinite number of rounds until you. So it's not a term of convergence of something like really many rounds, and you ask, okay, what can I exactly achieve after n rounds? But for some tasks, n has to go to infinity.
Okay, I see.
Okay, good. So now you may ask, what is possible under LOCC? And for the case of pure bipartite states, there's a very nice result that solves it. And actually it's surprising that it can be solved so easily. And this is sometimes called Nielsen's theorem because we proved it already 25 years ago. So you can ask, if I take one state and ask, can I go with LOCC to the another state? Then this is possible if and only if some of this Schmidt vector of this phi majorizes the Schmidt vector of psi. So this is a vector of the Schmidt coefficient. And what does this relation mean? This means that the biggest Schmidt coefficient of phi is larger than the biggest Schmidt coefficient of psi, and the sum of the two biggest ones is larger than the sum of the two biggest ones of psi, and so on. This is called as majorization, which is often known in probability theories in connection with entropies and so on. Yeah, and this result just means you can just look at the Schmidt coefficients and decide whether this translation from here to here is possible. Yeah, this is of course very nice, you can calculate it. Again, you may try to do the similar things for the multiplier case. And, okay, I just stated here more or less it's difficult. So there are some works on that, and I should stress, there's some beautiful works by the group from Barbara Kraus, by Olivier Vincent and Cornelia Spee and so on, where they did something and actually achieved partly full classification. But again, so the full classification for 4 qubits, I think the paper is 70 pages, and it contains a lot of special cases. Yeah, so it's not the thing that you, and it's only for 4 qubits. It's not general. Yeah, it's not somehow. It's not for general dimension. Yeah, so but that's why I'm just saying it's very difficult. Yeah. So, since this is so difficult to characterize, we can again look for some simplification. Here we can ask, what can we do somehow to coarse-grain the picture, to look maybe at larger transformations, and ask, okay, what can we achieve with this? And this is known as the so-called notion of SLOCC, which means stochastic LOCC. And what does stochastic mean? Stochastic means I do not care whether I arrive at this target state with probability 1, I just care whether there's a finite probability to arrive there. Yeah, so in principle, there might be, I may run some protocol, in the remaining cases, I may fail, but there's at least a finite probability that in one branch of the protocol, I succeed. Yeah, and this is somewhat, if this is possible, you can still say that these states are somewhat equivalent. At least if you have one copy of this state, at least there's a finite probability to reach this state. And this is, of course, more general, yeah, because if I don't restrict this probability of being 1, then somehow this is a more general classification. And the nice thing is that this can be mathematically very easily expressed. And this is the result by Otfried colleagues. So they showed the following. If you want to go from psi to phi with some SLOCC, that means just that there must be some matrices, ABC, such if I play this, it will be C2. This, I get this. So these are now arbitrary matrices. They are not local unitaries, because local unitaries, would be just, of course, deterministic. They would not change the norm and so on. Yeah, but this is arbitrary. Should be arbitrary matrices, and if I look at these matrices, they can go side to side. Of course, in general, they will not keep the normalization. Yeah, but okay, I can put the normalization in front. So, but this is some of the mathematical stuff. And this is very nice. And because this is now a clear definition which one can handle, one can do calculations, and that's somehow characterized. And actually, I will also show later that this is then quite related to some problems in mathematics, about tensor rank and so on, which I will explain in a second, which is essentially quite generous. Yeah. So, I mean, I don't know, shall I give you some argument why is this equivalent to this one? Yes. Is there only one person saying yes? Or? Roughly, the thing is like that. Okay. So roughly, if you would have such a protocol, you start with something like psi, you start with psi, and you want to go to phi. Then, in our picture before, this would correspond to such a protocol where it is a sequence of things. And this I can see as something like a protocol which branches for every measurement, because in every measurement I get some result, and depending on the result I do something else. So I can see this, that I start essentially as sometimes I start with psi, then maybe Alice makes a measurement, and then Bob gets some state. Out of psi 1, psi 2. And then Bob makes something, and I arrive at something like, I don't know, psi 3, psi 4, or depending here, I get something like psi 5, psi 6. So I can see this entire scheme if I don't care about the probabilities. And I just like, is there some probability to arrive at the final state? Something like that I start with my state, and in each measurement I branch depending on the result. And I'm just asking whether there's some, I don't know, I do it several times, several rounds, but at some point I want to arrive at my state phi. Yeah. And now you can ask, what does it mean? But the point is here, this is now something like this branching, this measurements, I always describe by a single matrix. Because this measurements is something like effects mapping the state to something. As Anna had these measurement operators, I talked before. So that means that there must be some path here which corresponds to certain things, and since these are local measurements, this corresponds to the product of certain matrices. And this essentially in the end gives you this. Yeah, I mean, okay, maybe this gives you some idea. Yeah, I see some people smiling. Yes?
If we do this, can we end up with phi which is entangled, or does it have to be like a very simple state? Because I don't know, in my mind every time I do a measurement I have to know simple physics.
But if you do a measurement, it does not, I mean, if you start with an entangled state and do these measurements, of course you can end up with an entangled state. And of course you can destroy entanglement. But it does not mean, or you can reduce the entanglement, but it does not mean that the measurement is, the entanglement is already destroyed as the first instance. Yeah, you can, for instance, see the following. I mean, maybe in the first step, Alice has her particle. Let's interact with some ancillar, and then measures the ancillar. This does not mean that the entanglement is completely lost. Yeah, but it may be it's reduced a little bit. So in this way, it means that here, so if this is separable, well, if this is separable, this will also be separable. Yeah, but these things can destroy the entanglement, but yeah, but in general they can they do not. I mean, it doesn't mean that it immediately lost. Actually, yes, and of course, now having this definition, you can ask, okay, let's assume that these things are invertible, these matrices. Then, of course, I can put the same definition onto the other side. And that means that they're really somewhat equivalent. I can go from psi to phi and from phi to psi. And this gives me an equivalence relation, and this I can study now. Yes?
What about dimensions of Hilbert spaces for the states E?
You're asking for the dimension of the Hilbert spaces.
Yeah.
Actually, okay, my examples will be always qubits, but actually this thing is completely general. I mean, for finite dimensions, I should say. For infinite dimensions, one maybe has to be careful. Yeah, but for finite dimensions, I mean, of course, the matrices are then bigger, but it's not really a difference. Good. So, now comes the first result. And the first result, or one of the main results, is the following: that if you take this GZ state and this W state, there's no way by S equals C to go from here to here. So in principle, these are two inequivalent forms of entanglement. You cannot go from this state to this state. This was one of the starting results in the field by Wolfgang Dürr, Tifel Vedal, and Nasser Iraq. And this actually, the name W state comes from Wolfgang. It's not, sometimes you hear that it's called Werner state, but it's not responsible for Werner. This is something that comes from Wolfgang. And so, and the title of the paper is 3 qubits can be entangled in 2 inequivalent ways. And this more or less takes everything. Yeah? So in principle, you can somehow, there's these 2 classes, and you cannot convert one into the other. And so they are inequivalent. And of course, for us, it means now that we should look for physical differences between these things. Yeah? In general, you can have something like 6 equivalence classes of entanglement for 3 qubits. Namely, you have this GZ class and you have the W class, but you have also these lower entanglement classes, for instance, fully separable states. Yeah, I mean, there are also some of them can be low, and you have sometimes these biseparable states, A versus BC, B versus AC, and C versus AB. And you can essentially go from the GZ class to any of these classes, and then further down to the fully separable class, but you can never go, these are not equivalent. You cannot go. And this is okay. And now you can ask, okay, what happens for 4 qubits? And there's a nice paper by Frank Verstraete, which has the title 4 qubits can be entangled in 9 different ways. But actually, the title is a little bit misleading because it's 9 times infinity. So in a sense, if you look, I mean, there are essentially infinitely many equivalence classes, but you can separate it into the 9 classes, but they have some continuous parameter. Yes, that's good. I will actually comment on this also a bit later, why this is the case. Okay. So, now you can ask, what is is there some deeper mathematical reason for that? Yeah, of course, this is not a physics question, but I mean, okay, still it may be interesting. And there's a notion of so-called tensor rank. What is the rank of a tensor? Actually, sometimes you hear that the rank of a tensor is just the number of indices. Yeah, in some communities like that, but I'm talking about a different kind of tensor. And it goes like follows. If you have something like a matrix, you can define the rank of a matrix by asking, I want to decompose it into matrices of rank 1, which are some vectors from vectors, some cross product of vectors, and I ask how many terms do I need. And you can easily see that this is nothing but the rank of a matrix. Yeah? So in principle, if you have a matrix of rank 2, there are 4 vectors, 2 A's and 2 B's, and you can write them as. Now we can just simply generalize it to tensors. So if you have 3 indices, you just ask, okay, how can I write it like that? And I just, okay, I take these things as a product of single index objects. Like that. This you can call tensor rank. Fine. It's a definition. Looks very innocent. Unfortunately, well, depends a little bit. It's very deep and it has essentially not much is known about that, although it's so simple. Why? So there are some things that you can observe. So one thing, for instance, this tensor rank differs whether you consider as overall real numbers or complex numbers. Meaning the following: if you take here something like a real tensor, but you allow them to be complex, then the rank may differ whether you allow them to be complex or real. Actually, it's not so surprising. In hindsight, if you once realize it, it's surprising that actually the normal matrix rank does not depend on it. If you have a real matrix, and you allow here for complex vectors, you cannot decompose it more efficiently. It's actually more surprising. Then, this tensor rank has very important applications in the field of matrix multiplication. Meaning the following: if you multiply two matrices, essentially, okay, you know how to do that. Well, let's assume, yeah. And naively, you would somehow see this as you just multiply all the indices, which means that you would need to make n-square multiplications. If you can, however, see this as something like a multiplication with a specific tensor, which more or less encodes this multiplication. And if you know this rank and have a simple decomposition, you can simplify the algorithms of matrix multiplication. And this was discovered by Strassen in the 70s, and actually this is now the basis for all these programs like Mathematica and MATLAB do the matrix multiplication. Can do it more efficiently than just multiplying simply the numbers that you would do by hand. And so this is obviously a quite important application. And of course, multiplying matrices is something what everyone, or every numerical algorithm does quite a lot. And this is very difficult to calculate, and I mean just, okay, it's not a proof, yeah, but for instance, there was quite recently a paper in Nature where they just used AI to calculate the tensor rank, yeah, because it's really difficult. There's no systematic algorithm to calculate the tensor rank, but they trained some AI to guess some tensor rank. They had some success. Or to guess the tensor decomposition. Okay, so this was not mathematics, I'm sorry for that. Yeah, but this has physical applications. Why? So, let's consider something like this, a pure state. I mean, essentially, this tensor rank decomposition is just asking for such a thing. I take my state and asking for the minimal decomposition in terms of product vectors, which is something like the split decomposition. This sounds spirit. However, these are not necessarily orthogonal. Yeah, but I can ask how many terms do I need if I want to decompose it into product vectors. And this quantity is obviously invariant under such transformation, because if you do such ABC, well, this changes the states, this changes this one, but still you have the same number of terms. So what do we learn from that? Let's look at the GZ and W set again. Yeah, question?
Why they don't have to be necessarily orthogonal?
Well, it's just in the definition. I mean, of course, I can require this, but I mean, in this definition, there's no relation between these things or these things. They're just arbitrary vectors or rank 1. Yeah, so I'm good. But now let's come to the SLOCC classification again. So, I mean, in this picture, you see that the GZ state, it has two terms. It has 0, 0, 0 plus 1, 1. It has two terms. So it has tensor rank 2. The W state, however, has tensor rank 3. And because it has 3 terms. You cannot go beyond that, because otherwise it would become essentially equivalent. Yeah, so you can see this difference between GZ and W state as something like a mathematical difference between tensor ranks. And you can also generalize it and make it something like a quantified entanglement, meaning the number of terms that you need in such a function. This is called the Schmidt function. Maybe as a final remark, which is a bit surprising at first point, but also again quite deep. So, if you take a GZ state, which is this state, I can apply some SLOCC transformation. And I can, for instance, apply this that I map this 0 to 0 plus epsilon 1, and so 1 to 0. And then I can map this state to this state. But now, if you let epsilon go to 0, then this term cancels, and essentially I get something like a W state, because in lowest order of epsilon I have a W. What does it mean? It means I can approximate a W state arbitrarily well by GZ type states. So I have these two families of states, this SLOCC class of the W state and the SLOCC class of the GZ states. And first they look just different classes, but they have a funny property that I can approximate every W state as close as I want with GZ states, which means they must be of measure 0. Yeah? And actually you can also see it that in this Schmidt-like decomposition that I had, if you put these parameters equal to 0, it would mean that they are somehow unexplainable. Okay. Questions? Yeah.
I'm a bit lost. Yeah. You said the complementary events. So it does not imply that the measure is 0, does it?
No, I'm just saying that so I mean we have these two classes, but actually the W class is much smaller than the GZ class in the sense it's of measure 0. Yeah, if you have something like a manifold, and the W class is something like a submanifold of lower dimension. And you can approximate everything in this submanifold arbitrarily well by this GZ states.
Yeah, but why does it have 0 measure? Is it because I'm lost?
Because, okay, if I talk about 0 measure, I should tell you what the measure in the state space is. I should tell you some more about the volume. But no, what I'm meaning is the following. Actually, you can see, maybe it's better to see it from this way. What one can prove is the following. That in this kind of Schmidt-like decomposition, this one. And these are all states can be written like that. And the general state, if you have arbitrary coefficients, belongs to this GZ class. But the W class is the case where theta is equal to 0 and lambda 4 is also equal to 0. So the W class is something like a 3-parameter subfamily of the entire state space, which has 5 parameters in this parameterization. Yeah, so that's what I mean with measure 0. Okay, good. Okay, let's come to this one. Yes. So, okay, I must also apologize because this is a bit mathematical. Good.
It's the other way around also true. If I start with a W state, I can go arbitrarily close to a GZ. Because the GZ is more entangled.
And we'll come to the question which is more entangled in the end. Yeah, because it depends what is more entanglement depends a little bit on how do you measure this. Yeah? But the other way is definitely not true, so because you can still see because the GZ states have 5 parameters and W states only 3 parameters. So cannot be possible. Yes?
Is there a conversion rate then? Could I take multiple copies of the W state and just get fewer GHZs at the end?
Yes. This is true. I mean, I should say, this is SLOCC is only defined on a single copy of quantum state. And this does not mean that what happens, does not imply much about what happens if you want to have K, W states and L, GZ states, what is possible. I mean, there works on that, but it's a different game. Yeah, so, yes. Yes.
So as soon as epsilon turns to 0, we leave the class of stochastic NOCC transformations, right? Is there like another class of transformations that we enter? Or?
Not really. I mean, okay, then just the matrices essentially become the matrices are not invertible anymore. So it would be somehow like more generally. Okay. Yes, it's not. It becomes something like. Actually, okay, one has to be careful because if they become not invertible, we have to take care of the normalization because then the normalization may go to infinity or go to 0 depending I would say you're leaving the serious basic transformations. Yes. Okay, good. Okay, so, this was not really mathematical. I can relax a little bit, and I will explain you why the GZ state is called the GZ state. Yeah, I mean, I talked about the W state so much, now about the GZ state. So, yeah, let's talk about the GZ, so-called GZ argument, and how you can derive Banach properties. So, roughly it goes like that. So, let's assume we have 3 particles. And we have a bunch of measurements, which we call just x and y, and which can have the measurement results plus minus 1. For the moment, you should not think of Pauli matrices. This will come later. They're just measurements. And now I can look at this expression, which is the product of the x's and always the product of 2 y's with 1 x. Yeah? Now, if you look at this product, you see that this times this is nothing but this. Because you can just multiply and you have this 2 y's, because y is plus minus 1, this 2 y's are cancel, and this is somehow. That means that it's impossible to have that these 3 terms are equal to minus 1, and that this times is plus 1, because these 3 terms give you as a product this one, and this product of 3 times minus 1 gives something like a minus 1 and not a plus. Yeah, so it's just algebraically impossible, or numbers plus minus 1, yeah, because of this relation, so that these are minus 1 and these are plus 1. That means this thing cannot be 4. And this means that, I mean, it cannot be 4, but the values are always plus minus 1, so actually the best thing what can we have is that it's 2, because one of them must be really minus 1. And so that means that essentially we had something like this result, that this terms of measurement value should be smaller than 2. This inequality has a name. This is called the Mermin inequality. So, once you have this, okay, so far there was no quantum mechanics involved. So you may now look somehow into what happens in quantum mechanics. And then I have to specify a little bit which state I'm looking at, which measurement. So far there was no constraint on the measurement, as I said. You should not think of Pauli matrices. So, let's go to quantum mechanics, and now consider the GZ state again. Here it is. And now take the Pauli matrices. And you can easily check that the GZ state is an eigenstate of these Pauli matrices. Meaning the following: if you apply x, you essentially always flip the zeros to 1, so you flip these 2 terms. And if you apply something like z, you get this term gets 2 times the minus sign, which essentially disappears. So this is actually a quite nice relation. That means we can actually define the GZ state by being an eigenstate of certain tensor products of Paulis. And this will become later. We will talk in the 3rd lecture. I will talk about graph states, and they are more or less defined also by this property. And yes, so that's somehow. That can generalize the GZ state by trying to get similar properties. Okay, but now let's look further for these operators. I mean, the GZ state is an eigenstate of this thing and this thing, so it's also an eigenstate of the product. And now if it's the product of these 2 things is just minus yx. So this means that if you take a GZ set, the expectation of this guy with a minus sign is plus 1. And now you insert it here. You can see this is plus 1, this is with a minus sign is a plus 1, this is a plus 1, this is a plus 1, so it's 4. So obviously the GZ state violates the inequality, this Mermin inequality that I showed you before. So from this you see, oops, there must have been some mistake. Or I mean, I derived this inequality. No one of you protested actually. I should have maybe asked more specifically, yeah, but sorry, there was no protest here. Now I'm telling you, well, okay, if you take the GZ and this measurement, you get a different value. So the first thing that you can maybe do in this such a case, you run to the just measure it. And people have done this. And actually, a very old experiment by Jan Pan and Anton Zeile in 1999 already, they clearly saw at least it's a value of 2.8, which is larger than 2. Yeah, so it's some more hint that maybe there's really something wrong with this number inequality. And you also see, I mean, okay, current experiments really achieve a value of 4. Yeah, so I mean, this is an old, very old experiment, but nowadays you can do much better. So, what's wrong? Still, what's wrong in this state? What's wrong in this relations inequality? So, if you look more carefully, when we proved this, we have made 2 assumptions. One was that we said, okay, all these measurements have values plus minus 1, independently of whether they are really measured or not. Meaning, I combine these things, but of course in a single experimental run, I have to decide whether I measure this one, or this one, or this one. But I just said, okay, I combine them and always say, well, this must be plus minus 1, independent of whether I measure it or not. This was an assumption that I made, and this is sometimes called realism. And I also assumed that the value of, for instance, x1 in this term and in this term is the same, although Bob measures something else. Which means that the value of Alice does not depend what Bob decides to measure. This thing is often called locality or non-signal. This was also an assumption. And what you essentially can learn from this example is that, well, one of these assumptions must be wrong. Yeah, because somehow, well, it's not only that quantum mechanics neglect this assumption because quantum mechanics predicts something different, but also the experiment tells you, oops, there must be something wrong. And nowadays you can also say that this means that sometimes the GZ states are non-local, meaning in the sense of violation of value inequalities in some extreme manner, because they really give you something like, you have an inequality with 4 terms, you get something like, and you get this so-called algebraic maximum, meaning that you get this value of 4. If you compare it with this, maybe you know this CSS inequality, yeah, where you also have 4 terms, but quantum mechanics gives you maximally a value of 2 times square root of 2, which is 2.8, which is not the algebraic maximum. Yeah, but here it's more or less really much larger, and this minus something. You can see there's something like extreme violation. Questions? I mean, one thing, of course, later will be then for graph states. You have other states which are somewhat defined by this eigenvalue equation, and then you can also again try to write in value inequalities. Yeah, similar. Okay, good. So let's talk finally about some other properties of the W state. And one thing to mention is the role of the reduced density matrices. If you take a GZ state, the 2 body marginals are separate. Yeah? Meaning that if you trace out one particle, you get this state, and as Anna has explained to you this morning, this is something with a certain probability you get certain product states, so this is something like a separable decomposition. And this means that this is a separable state. For the W state, you can also calculate this reduced density matrix, and you will easily see that it's entangled. And this, for instance, we can do by these PPT criteria that was mentioned this morning. There are a lot of entanglement criteria, just see it's entangled. I don't want to do the calculation, it's too detailed. And you can even prove that the W state has something like the maximal entanglement in the reduced states. You cannot have more. Yeah, and this is something like a different property that if you throw away some for one particle from the GZ state, then you lose all the entanglement, and for the W state, it's not the case. It's more robust. And sometimes this is also visualized in this form. Yeah, so this is Borromean rings, of course. So they have 3 rings, and they are somehow intertwined. But if you remove one of the rings, then the 2 others are not connected. Okay. Finally, you may ask, okay, how can I generalize this? I will talk about this in much more detail on Saturday, but I just say, okay, you can of course write down GZ states for 4 particles, you can write down W states for 4 particles, There's something like a cluster state, which we'll explain, which is something like also a generalization of the jet Z state because it's an eigenstate of Pauli operators. And you can have Dicker states where you have two excitations distributed over the particles, or something also unitary invariant singlet states, which also. So you can, if you go to more particles, there's an entire zoo of new states, and yes, this will be verified. Good. Let's come to the next part, and now let's try to go a little bit beyond 3 qubits. So what can we say? I mean, this part was mainly about 3 qubits, and it was already complicated enough. Yes?
What is that picture? What's the picture?
This is a small mountain also close to Siegen. It's called Rügenstein. So actually, okay, it looks more impressive than it is. This is more or less saying it's just a forest and some, okay, this is some old volcano, some rock from an old volcano, but it's not real. Good. So, what happens for more than particles? First, of course, you can make similar classifications. Yeah, you can ask them how many things I can split it. You can have it, for instance, fully separable. You can have a tripartition where you have 2 entanglement, but Alice, Bob are separated, and Bob and Charlie and Dave are entangled. You can have biseparable states, but you can have something what is again called genuine multiple. And in all these classes we can define again. Yes?
What does 3-separable mean?
3-separable means that there's a tripartition of the 4 particles where there's no entanglement. So in this picture it means something like so you have something like 4 particles, but I can basically group them together. So it's a tripartition in 3 parties where there's no entanglement, but there's maybe entanglement between these 2 guys. Okay. Now, if you want to do the same program as for 3 qubits, you will run into problems. And you can see the problem from a very simple parameter counting argument. Namely, what you want to maybe ask. Okay, you ask some states, you apply some transformation, maybe local unitaries, maybe S equals to C, maybe whatever. If you ask how simple can I make this state under such transformations? And the point is that this kind of transformations doesn't give you enough parameters, because this number of parameters from the T scales only linearly in the number of particles. Because maybe every T has, I don't know, 10 parameters, and if you have 10 particles, you have 10 times 10 parameters. But the dimension of this thing, or this state, scales exponentially. And because the number of states, or the parameters for states, is exponentially the dimension of Snell's space. And this means, if you want to do such kind of simplification, may these be local unitaries, or S equals to C, or whatever, this will always give you, or typically give you something like a continuous family of equivalence classes, just from the parameter count. And from that, it should also not be a surprise that for the 4 qubits, you find infinitely many S equals to C classes, as I mentioned before. Yeah, because I mean, it's just the parameters. So, good. Then, there's still something like, however, as a result, how you can decide the LU classification for LU equivalence classification for qubits, which is again looking at the margins that we had several times before. And yes. So, let's look now at maybe the last 10 minutes. I will look at one question that people look at if you go to more than 4 particles. And this is something like the quest for so-called maximally entangled states. Now you can ask, okay, what is maximally entangled? One can debate about it. Yeah? But there's one definition that you can easily apply. And this was essentially brought forward in this paper. It's the following. For bipartite states, we know that the state is maximally entangled if some of the reduced states are maximally mixed. Now the question is, can we, for instance, find some multipartite state which has the same property for all bipartitions? So for instance, I have a 4-particle state, and you can use this plot here, I said it before. So these are my 4 particles. Now can I find a state that is maximally entangled for this split, that is maximally entangled for this split, and this is maximally entangled for this split versus the other things? Yeah, so I mean, I can have a 4-partite state. I can look at AB versus CD, I can look at AD versus BC, and I finally it's a third bipartition. I can ask, can I make it maximally entangled for all these things? And interestingly, this paper already quite early proved that this is for 4 qubits is not possible. Cannot do it. That's just, I mean, you can write down the condition, doesn't work. More or less this you can do by brute force calculation. But now you can ask, okay, what happens for more general states? Can I do this or not? And this is a problem of so-called absolutely maximally entangled states. So actually, I'm apologizing for this name. Yeah, I found it ridiculous. Absolutely maximally entangled. This is really something, yeah? It was not invented by us, but I just use it because the community tells it like that. Yeah? So, anyway, but it's just the same question. Yeah? Can I find something like an n-particle state where all the reduced states on half of the particles are maximally mixed, yeah, which means it's a maximally entangled for the bipartition. Yeah, and this is a question, and there are some examples known for the Bell states, obviously. Jet Z state will also do the job. For 5 qubits and for 6 qubits, you also find some states, which are so-called graph states. I will explain these symbols in the end, but for the moment, just know that they exist. And the question is, do they exist? Yes, they correspond to say interesting, they correspond to some quantum codes. And for instance, one question that was more or less open for 20 years is the following. These states exist for 2, 3, 4, 5, and 6 qubits, and not for large and 8 qubits, but what happens for 7 qubits? And just give you to think, so one thing, what can prove that really for 7 qubits they don't exist, but you can find something like a best approximation. Meaning that you have some 7 qubit states, and at least 32 of the 35 3-body density matrices are maximally mixed. You can write down the state, but you cannot make all of them. And another thing that was more recently is the existence of the so-called AME states of 4 particles with dimension 6, which sounds a little bit artificial. Yeah, why do you want to do that? But actually this has something like a geometric interpretation. So they are so-called orthogonal Latin squares, which means the following. This is a square, and you have some chess figures there, and you also play chess, I should advertise this. And these chess figures have different colors. We have 5 different colors and 5 different types of things. And this square is a rule that in each row and each column you only have exactly one color and exactly one type of things. Now you can do the same thing for 6 times 6 squares. You take a 6, another chess figure, there's actually the pawn is missing, you can use it. Yeah, and then use some 6 color, can you also find it. And actually already Euler remarked that this is not possible. This was proven later that it's really not possible. But actually for 7 times 7 and for 8 times 8 you can find it again, for any other dimension. So this was something like a coincidence. And actually one can show that this IME state exists, and one can see something like a quantum version of this problem. In a sense, you do not look for complete permutation that has certain properties, but you look for certain unitary matrix. And this was, actually this problem is somewhat nice. You can see some popular stuff about it. Actually, there's a paper by the Wodetskis, or Pavel Wodetsky and Tarachowski and some others, about 5 important problems in quantum information theory, which I can recommend you to read. And they noted 5 problems, and if you solve one of them, you will get money. And the money that you get depends on the year that you solve it. So if you solve it this year, then you will get 2,025 euro. If you wait until next year, you will get 2,026 euros. But of course, I mean, if you wait, there's a risk that someone else solves it. You cannot calculate somehow the probability of solving it. But anyways, yeah, and this was one of these problems, and this was an answer. Good. One can, of course, look for more general things, and finally, there's some things like many tables for the AME state. They can prove in the blue things they don't exist. And in this, where this E, they exist, and you see that this table is a little bit outdated because for 4 particles in 6 dimensions this is empty. But now there's no this one that exists. Okay, maybe this is a good point to stop. My next section would be about entanglement measures, but this I then can give on Friday. Yes, maybe let's jump shortly to the conclusion. This one, yes. So I think what we can learn from the things that what I explained today is first, there is no such a thing like a maximum entangled state for multi-particle systems. Depending on the properties that you want, you find different states that are very interesting. And also what I maybe showed you when I talked about this tensor rank and so on, that really this multi-particle entanglement is closely related to fundamental problems in mathematics, which look very innocent, like this tensor rank. Yeah, you can easily write it down, but actually, if you really think about it, it's extremely hard. And this, for me personally, I found quite fascinating. That you sometimes have because you know all this linear, you probably all had some linear algebra problems. And they always tell you, oh, things like eigenvalues are well solved in 100 years. Yeah, but for instance, if you think about the eigenvalue of a tensor, I mean, this is what mathematicians are discussing nowadays. Yeah, so it's really there are a lot of things. Thanks for your attention.
Thank you, Otfried, for your nice lecture. So, do you have questions? We have time.
Thank you very much for the talk. I have a question about the characterization of the operations for more than 3 parties. Is there any characterization, kind of an instance theorem or this log characterization for 3 parties?
So there are, I mean, in terms of this LOCC, there are some results. I mentioned them shortly somewhere here. Okay, sorry. So there are some, I mean, this one, yeah. So this is the Mears result, and if the point is, if you would like to go to multi-particle systems, then if you have one of these 3 parties, and you want to 3 parties, and you make an LOCC transformation, then this, of course, is also an LOCC transformation with respect to this bipartition. Yeah, because I mean, if I just GC them together, I mean, if I make some local operation on the 3 parties, this is also local if I would put them together. So that means that Nielsen's theorem has to apply. This puts some constraints. But also it holds if you look at this bipartition, this particular. So also Nielsen's theorem puts some constraints. And also there's a third bipartition. But this means you get already a lot of constraints. And what is then the typical result? And this is one of what's mentioned here, that actually typically from LOCC you cannot go anywhere. Because there are so many constraints, especially if you go to 4 and 5 particles from all these bipartitions already, that more or less not much remains. And all the states, they call them, partly in this verse of Barbara Krauss, they call it isolated. In the sense, okay, this is some state, you can not reach many states from that, apart from local unitaries, but you can also, the state cannot be reached by other states, so some isolated state. This is the general case for multi-particle systems. Yes?
Is the fact that you can, I don't want to confuse the story, you can,
Second, was it approximate GHZ from W or the other way around? GHZ from W, right?
No, I can approximate any W-type state from GHZ.
Okay. Is this somehow equivalent to the fact that they have the same border rank if you sequence tensors?
Okay, I didn't want to mention the notion of border rank. I mean, okay. In some sense, yes. The border rank is something like, I mean, okay. What you see in this example that we had. That, I mean, the W state has tensor rank 3, but it can be approximated well by tensors of tensor rank 2. And this is called the border rank, and asked what can be approximated. And actually, this is also a difference to this between matrices and tensors, that for matrices you don't have this difference. Yeah? But you can really see that somehow the border rank for 3 qubits is 2, because you can approximate every distinguished states of tensor rank 2.
You just said that LOCC is not very powerful. What changes when you allow for one global measurement in the end? I'm thinking of all these communication protocols where you can do everything and then in the end all qubits are collected.
What do you mean by one global measurement?
Across all qubits, like a band measurement on the system.
Good question. I don't know. I mean, so you think you make first an LOCC protocol, and then after all the LOCCs, all the parties maybe prepare some ancillas, and at the end, you allow some global measurements on the ancillas, and then you look what remains.
Yeah, like in communication, in the end, everyone sends the qubits to Alice, and Alice can measure across all of them, but just once in the end. Is this then increasingly more powerful or just marginally?
I mean, it must be increasingly more powerful, it must be, because there's some additional stuff.
Yeah.
Yeah, that's a good question. I mean, probably some people have thought about that, so I don't know. That's an interesting issue. If you run one round and maybe on ancillas make something like a non-local operation. But only one round at the end.
Thank you.
Yes.
Thank you for the lecture. We saw yesterday that if you have two bipartite qubits, we can transmit more than two classical bits of information. How this goes for multipartite qubits?
Meaning the following: you distribute some multipartite states, and now you ask, how can I use this to send or to make some measurements and send some qubit, and to make some enhanced classical communication? I think, good question. I think there are works on how to make some, you want to make some generalized superdense coding. Yes, I understand correctly. Yeah. I think there are some works, but I think it's probably in general it's difficult because again, it strongly depends on the state. I do not know what's the best 3 qubit state that I can use. And it probably depends whether I want to send just from Alice to Bob and Charlie. I mean, that's broadcasting scenario. When you want to send one party to 2 others, or Alice decides whether he wants to send to Bob or wants to send to Charlie. It probably depends. I do not know many details about that.
Okay, thank you.
Thanks for the lecture. If you consider the definition of maximally entangled state with the marginals, can you have a mixed state of 4 qubits?
Yes, sure. Because for instance, if you take just the maximum mixed state, it fulfills this, because all the margins are also maximally mixed. But this, I mean, the point is that this saying that if the margins are maximally mixed, this is only a sign of entanglement for pure states. Therefore, for mixed states, I mean, you can have always a maximally mixed state, but also the margin of maximally mixed, but of course the state has no entanglement at all. Yeah, so that's why only I have to put this constraint of being pure, then this only makes sense.
concerning this slide, and also, does the GHZ states, do they form a full measure set? Is it true for every dimension?
Well, the point is that, so, as mentioned, if you go to a higher dimensions or to more particles, you don't have this simple two binary choice between GZ and W. Yeah? So, it's a good question. I think in general, I mean, okay, we have an infinite number of classes, but I think typically some of them are still a full measure, I think. I mean, but I think it's difficult to make general statements. So for instance, there is for, if you go to a 2, you have something like 3 qubits, like 2 times 2 times 2. There are some scenarios like, for instance, 2 times 3 times 3, where you still have a finite set of S velocity C classes. And in these instances, it's also known that there's one class which more or less can approximate everything. It's something like the generic class. But I think it's difficult to make statements about n qubits in general, because you have an infinite number of classes and so on. And then I'm not sure whether there's always results stating that there must be one class which you can use a full measure where you can reach everything. I think it's probably not true. Does that answer?
Yes, it does. Another question. Do you have some intuition about the full measure class having like rank 2? It's not full rank because it goes against my intuition.
Yes. Actually, this is one of the things why tensor rank is also very peculiar. Because naturally you would always think that the generic state is full rank, like for matrices. A generic matrix is full rank, period. Yeah? It is different. And actually, this is also one of the points why it's numerically so difficult. Yeah, because this result essentially tells you it's not enough to make some approximative numerics. Because if you try to approximate something, you may find a very good approximation which tensor rank 2. Yeah, so, but still the things of tensor rank 3. Yeah, it's counterintuitive, I completely agree. But sorry, it's also...
so you lost the upper continuity in the tensor rank, right?
Yes. So it's also not intuitive.
Okay, thank you.
Thank you for your questions. Maybe you can stop now and keep discussing during the coffee break. So let's take Otfried again. No announcements, no.
Eu vou te dizer que não entendeu nada, porque ninguém tá